Okay, good morning. Good morning. Hey. Good. Okay, so any questions before we get started? Anything about the course or anything that isn't making sense? It's all okay? We're all at peace? Okay, good. Okay, so the worksheet. So this week we were talking about, mainly about determinant and trace and stuff, and in a way, this week we spent a lot of time developing a theory that in principle you sort of already know, so that's kind of, but sometimes we have to do that kind of stuff. So I don't know if we know a huge amount more at the end of this week's lectures, except that we hopefully know that how determinant, it's a little bit trickier than maybe you first think, and anyway, now you know how to go about it. And while, there are some textbooks that try to avoid using determinants much, but it's going to be in reality it's pretty hard to do so. Like once we start looking at eigenvalues and generalized eigenspaces and all this kind of stuff, det A minus lambda I don't know, we sort of can't really get away from it. Anyway, so we know about determinant. We also talked about transition matrices, we call them, change of basis matrices. And that's what this first question is about. The first question, it's a little bit silly, this first question in a way. Just a comment here, I've done the same sort of mistake I made in the lecture. This is when V is Fn. To be able to write out the matrices. But anyway, in this question, there's not much to do actually. So in this question, we're given the information we're given is a field, a basis. So it'd be F2 in this, two-dimensional space over F2 in this case, because the basis has these two elements. And what we're given, it's a bit confusing. So we're given this vector V we're given it in the basis B. So it's 1 times that plus 1 times that. That's what it means. So we're given V as, just to say that again, these guys are vectors in Fn. These guys are also in Fn, but they're in Fn with respect to a different basis. They're the coordinate vectors of V with respect to that basis B over there. And what we're asked to compute is the transition matrix. This question's picked to be easy, that it's the transition matrix from the standard basis to the basis B. And then, we gaze up at our formula up here, and if that was the standard basis, that's just the identity matrix, so it's just B. So there's nothing to do almost, so we'll kind of skip through this fairly quickly. This matrix, this is just B. So there's not much to do. So it's 1, 1, 0, 1. But there is a little bit, sort of a little bit to do here. What you're being asked to do here is to find find V in the standard basis now. So that would be, in the same basis that this B is being written in, the standard basis. So, okay, this is slight confusion. So we're trying to find V, basically, in the standard basis. And, we just use our little formula up right at the top there. That V in the basis A is just this transition matrix times V in the basis B. So this is just none other than our B times the guy that we're given, VB, like that. So there's almost nothing to do. Okay, you just do that for all the questions. So this is going to be 1, 0, 1, 1 times 1, 1. And that's 1, 0, because we're working over F2. Okay, that 1 plus 1 is 0. Good. So anyway, that I mean, but at the same time, it's like I should change this question. It's a little bit silly because we can just work out as well. I mean, 1 times this guy plus 1 times this guy, we can just, work it out. It's this first standard basis vector. So it's not very helpful. It would have been a better question if we weren't using the standard basis for this guy. If this was a given 2 bases and we had to actually do some work. So having said that, I think I'll skip this question because I should change it. But anyway, do same thing for all of them. But let's go to these other ones. So here we've got we're working with determinants and traces as well of some endomorphisms. And, well, we know how to find a determinant of a matrix, of course, and similarly the trace of a matrix. Remember, trace is less familiar. Remember, it's just the sum of the diagonal entries of the matrix. But now we're doing it for endomorphisms, but the only trick or whatever, or the practice, is we have to pick a basis for each of the vector spaces in question here, a simple, like the basis that's easiest to work with as possible, probably. Write out the matrix of each of these linear transformations, these endomorphisms, with respect to that basis, same basis in domain and codomain, and then just compute determinants and traces. Okay? Yeah. So let's indeed do that for some. That's good practice anyway of just finding matrix representations, which is like important. Let's do it down here. Oh, there's lots of out of page. Okay, so let's do that. I'll look at the questions here because I can just read them. So the first one we were looking at, V was R. So it was polynomials of degree less than or equal to 2 with real coefficients. And theta of F was XF prime. Okay. If you're working with polynomials, we'll probably use the basis. We can use any basis, but why not use 1x squared? Anything else seems a bit, well, will just make us work a bit harder, probably. Okay, so then we have to work out the matrix. So, I don't know, I would just do it by computing theta of each of the basis elements and writing it back in terms of the basis elements, and that'll give my columns, boop, 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 3 columns. So this is 0. So it's 0 times 1 plus 0 times x plus 0 times x squared. Theta of x is x. Just using the formula. And theta of x squared, I get 2, so I get 2x squared. So our matrix representation of theta with respect to our 2 bases is 0, 0, 0, 0, 1, 0, 0, 0, 2. So it has determinant 0. Oops. And the trace of theta is 3. Of course, you could compute the determinant in this case another way by just checking that theta is not an isomorphism, for example, and then you know that it's determinant 0 automatically because it's not invertible. So theta is not injective, as theta of 1 equals theta of 0 are both 0. We know theta not invertible. So we could compute the determinant without having to, actually do anything, really. Oh, well, that's a special case because it was actually not invertible. If it is invertible, I don't think there's any cheap way of finding the determinant, more or less. You just sort of have to calculate it, I guess. I mean, I don't know if there's much difference between something have determinant 2 or 3, if you can see it. Oh, sorry, maybe I should go back and pick the questions, actually. It's maybe more helpful. Okay, so for this next one, so they're all pretty similar, of course. So for the next one, I guess we'll use the basis. We could either use cosh and shine if we want, but maybe it's easier to use the basis that's sort of given to us, e to the x, e to the minus x. Okay, first of all, they are linearly independent. Just, write a times the first one plus b times the second one equals 0 and plug in a few different values of x, and you'll see that the coefficients are both 0. Okay, then. So off we go. So theta of, just using the rule, theta of e to the x is apparently cosh, which is a half e to the x plus e to the minus x. And theta of e to the minus x is, by the rule, shine, which is a half e to the x minus e to the minus x, I think. So we've got our matrix. That'd be a half, a half, a half, minus a half. So in this case, the determinant is, we just make the calculation, minus a quarter, minus a quarter, minus a quarter plus, sorry, minus a quarter, which is minus a half, I think. And this time, trace is 0. I don't know if there's a way of knowing that the trace is 0 without making a calculation. Not sure. All right, so they're all pretty much the same kind of stuff. Let's skip the next one and move on to, maybe we'll look at the one with composition. So I guess we have to do the previous two first. So the rotation one, which I guess is part D. So rotation by alpha radians counterclockwise. I think that's the one where that's theta of xy equals cos theta. Where's sine theta minus sine theta down here? Cos theta. I think that's the one. I forget where everything is. We worked it out at some stage. Maybe we could check. So the rotation by, if I want to do pi on 2, counterclockwise is going that way. Counterclockwise, is that what it says? Yep. So if I put pi on 2, let's check. Cos of pi on 2 is 0. Sine of pi on 2 is 1. And that should take the e, like the x, to the y. Except, so these ones are isomorphic to complex numbers of modulus 1 because the a and the b here are forced to be cos and sine. Yep, if we had a, b minus b, that was complex numbers. These are forced to have a squared plus b squared equals 1, so modulus 1. Good. Yeah, it is indeed. So this equals, and I think we did it right. Oh, we did it wrong. This is -1, 0. So I think I need the minus sign there. Anyway. Now have I got it right? Yeah, now I've got it right. Oh, no, I haven't. I meant to move it to the y-axis. What have I done wrong? Oh, yeah, I did have it right. I just wrote the 1 in the wrong place. Okay, so that's moving this to here. So that's probably right. And, okay, so that's it. That's the matrix. We've had to work it out a little bit by, maybe it's a good exercise. We should have just worked this out by saying, oh, no, I don't want to work it out again. We did that in the lecture. There was a recorded lecture. Like we actually drew the angles and all that kind of stuff. I don't want to do that. So that's the matrix representation with respect to the standard basis of R2. And now we can work out trace and determinant. Trace is 2 cosine theta, and determinant is that by that minus that by that, which is 1. Okay. Good. And theta is meant to be alpha, anyway, in the question. E, orthogonal reflection in the line y equals x. That one we worked out in a tute, and I can do that one nice and easily. That one, let's see what it does to the standard basis vectors, E1 and E2. Well, it maps E1 to E2 and E2 to E1. So theta of E1 is E2, theta of E2 is E1. So the matrix representation of theta in the standard basis is what it is, 0, 1, 1, 0. So this one has 0 trace and determinant -1. Good. But now we'll do the next bit, which says composition of these two things. But I guess the question's not well formed because it just says composition. There's an order that we can compose the things in, of course. And it won't matter for the trace because trace of AB equals trace of BA. But, and it also won't matter for determinant because determinant of AB equals determinant of A times determinant of B. So actually, even though the question is sort of ambiguous which order to compose, it doesn't matter for the trace nor the determinant. So call them theta 1 and theta 2 or something. So the trace of AB equals trace of BA, and determinant of AB equals determinant A det B. Tells us that it doesn't matter about which order we compose. Now, if we use different bases for the two previous questions, we couldn't just, we're not allowed to do the matrix. The composition doesn't behave as matrix multiplication anymore. So then we have to worry a little bit more, maybe, but I guess not because the trace. So let me say this two ways. So first of all, if we use two different bases for the two parts, we'd be worried that the composition can't be just computed as the sum of the, as the product of the two matrices. However, we know that trace and determinant are both independent of the basis. So even if we used a different basis for A and B, we still know the values of their determinants and traces. And now we don't have to even do any working here, just say, even if we use different bases here, now use the same basis without having to do the working, we still know that this happens, and that one we're going to have to actually do. Sorry, trace we'll still have to work out. So I'll just say it another way. The trace of determinant of AB is just determined by determinant of A and determinant of B. Trace of AB is not determined just by trace of A and trace of B alone. Okay, like, you know, you can't write that expression in terms of purely trace of A and trace of B. So we do have to do a calculation. Anyway, we did use the same basis. We used the standard basis in both questions. In any case, we know that the determinant of θ1 composed with θ2, or the other way round, we know that's just det θ1, det θ2, and we work that out as something 1 times minus 1. For the trace, we really have to do some work. In the standard basis, this is, let's get our signs right, there they were, cos minus sine, sine, cos, and then this guy, so that's by that plus that by that. So this is trace 0. Okay, but I don't see if we can work it out. Even though we knew that one was trace 0, I don't think that tells us the answer. No, I don't know. All right. Okay, so that's great. So those questions are reasonable enough. Any questions about determinants, traces of linear operators? Yeah.
I'm just curious because I know I'm saying something about the determinant representing some sort of area.
Yeah.
The rotation matrix, we got the determinant 1. Was that because the area stays, like, was something that the area spanned by?
Yeah. So, yeah, one way of thinking of that, if you, for example, maybe I'm not going to explain this the best way off the top of my head, but if you look at a matrix, let's say a real matrix over the reals, and let's say it was diagonalizable over the reals, so we had all real eigenvalues, then these eigenvalues tell you how much, and then you look at the eigenvector, it tells you how much it scales that vector, whether it multiplies by 2 or whatever. So in that direction, it's telling you something about what the matrix, if you're talking about real numbers, so to talk about areas, we should be saying real numbers, it's telling us something about a scaling in that direction. But you could now look at the parallelogram spanned by the, let's say it's in R2, so we've got our 2 eigenvectors. Look at the parallelogram spanned by that, and the area of that parallelogram is now going to be the product of take that parallelogram and look at what the matrix does to it. It's going to multiply it by lambda 1, lambda 2, okay, or something like that. And yeah, because it's just multiplied on. And so yeah, I mean, in some ways, in a real matrix that's diagonalizable anyway, the determinant is telling you something about what happens to this parallelogram spanned by the eigenvectors. And I guess in this case over here, the one we're looking at there, yeah, so this doesn't have any real eigenvectors, right, because you're rotating the matrix. So you have to extend to the complex numbers, and it's a bit harder to maybe think of it. But it is still sort of, it is an area-preserving thing, this guy, because it rotates. So I'm sure you can think of it a bit better than, you don't necessarily need to have the eigenvalues to have this interpretation of determinant in terms of scaling. But that was the easiest way for me to explain it.
And is there any geometric significance of the trace, or is it just like a...
Good question. So the trace, off the top of my head, like in R2, let's think in R2, it's the sum of the let's assume that everything's diagonalizable for a few minutes. It's the sum of the 2 eigenvalues. So Yeah, I'm not sure if that tells us. Somehow the product of the eigenvalues is a bit better. I can interpret that in areas, but the sum of the eigenvalues? Yeah. Not sure off the top of my head. Like, I'm sure you could massage it into some kind of geometric statement, but I'm not sure. Yeah, I mean, you can already see, so, I mean, those things we just talked about, we'll come back to that one. I mean, the problem is, of course, not all matrices are diagonalizable, so we have to work a lot harder. But in the case when you've got a diagonalizable matrix, then, you know, like there's a P, D, P inverse. I mean, you can write your matrix like that. And the D is just all the eigenvalues. So then, because the determinant multiplies out, you know, the P and the P inverse just disappear, so you get the determinant of those guys, so you just get the sum of the eigenvalues. And similarly for the trace, because trace is basis independent, or because you can do trace of A, B, C equals trace of B, C, A, I mean, you can pop the P and the P inverse next to each other. So the trace is the same as the trace of this diagonal matrix, that's the sum of the eigenvalues. So that, just to explain that trace and when the matrix is diagonalizable, determinant is the product of the eigenvalues and the trace is the sum of the eigenvalues. We'll mention that again later on. If the matrix isn't diagonalizable or doesn't have eigenvalues, then that's of course not true. I mean, you can have a matrix that just doesn't have eigenvalues in the field that you're looking in. You can always extend to a bigger field, like an algebraically closed field, but if you're wanting to live in a finite field with 3 elements, you just force that the some matrices don't have eigenvalues. All right, I like these questions, true or false ones. So if the square matrix contains a 0 row, then det A is 0. True or false? True, and it is indeed true. So I'll put maybe I won't use red because it looks like it's wrong. I'll put a green tick. True. The determinant is the unique function that is both row linear and satisfies the adjacent row property. Yeah, false, good, because we need also the normalization. Because any multiple of the determinant will also satisfy those two properties. If that equals that, okay, this one we're going to have to do some work. It's not that easy to see, sort of cleverly done. It's not that easy to see how you could work out the determinant of A, B, C, D, E, F, 3, 4, 5 from that other guy. Let's do that. Oh, so I need some space. So I need to look at the matrix. And I might even need to look at my solution a little bit. So here we're trying to work out the determinant of this guy. And we know those other two determinants that you can see on the screen over there. So I think if the other two determinants both have the numbers 1, 1, 1 or 1, 2, 3, all in either the second row or second column. So it seems like a sensible idea already to swap the second and third rows, and we'll just use properties of determinant as we go. So I'm swapping 2 rows, so I multiply by -1. And now I have to do something. I have to try to turn a 3, 4, 5 into, well, 1, 2, 3s. But so this is going to be the row linear, and somehow by using transposers, I'm going to be able to use 1, 1, 1s as well. So I probably need to use the row linear property here. So now I'll write, 3 equals 2 plus 1. I mean, no, not being too smart there. And 4 equals 2 plus 2, and 5 equals 2 plus 3. So that middle row there is a sum of, it's the row 2, 2, 2 plus the row 1, 2, 3. 2, 2, 2 plus, so, I mean, maybe write it that way. So the vector, and I'll write it as a row vector, 3, 4, 5 equals 2, 2, 2 plus 1, 2, 3. And maybe that's even better to write it as 2 times that, 2 times 1, 1, 1 plus 1, 2, 3. So using row linearity, this is going to be, there's still the minus sign, but then it'll be twice det of A, B, C, 1, 1, 1, D, E, F, plus det A, B, C, 1, 2, 3, D, E, F. And now we're in business. We have to do a transpose now. Transpose. And we get minus 2 det. So transposing doesn't change anything. So A, B, C, 1, 1, 1, D, E, F. And now minus sign here. Det of the other guy. A, B, C, 1, 2, 3, D, E, F. And I think they're the ones we were given. So it's minus 2 times minus 1 and minus 4, which is minus 2. So after all that work, the answer is anyway false. So it's all right. It's false because it's minus 2, not minus 4. Okay. Right, see what we've done there. So it's a bit tricky sometimes to convert those things. So that's actually false. It is, what did we say it was? Minus 2. If determinant of A is not 0, then the columns of A are a basis of Fn.
There's no linear dependence between the rows. So, and it's yeah, is it true?
It is indeed true. It is indeed true.
They're linearly independent, and it's an n-line matrix, so they span Fn.
Good. Yep. So there's various, various ways of thinking through the logic of this, but yeah, I mean, first of all, to just say it as it's written, that's something good to just have off the top of your head. Determinant being non-zero means the columns are a basis. The rows are also a basis. Everyone's a basis. But a way to see that perhaps is that various ways. So if the determinant is non-zero, then its reduced row echelon form is the identity. So its rank is n, dimension of the column space. So its nullity is nothing, is 0 by the rank nullity theorem. So it's injective, therefore it's surjective, and okay, done. Or, so that's one way. Or determinant of A is non-zero means it's invertible, so it maps a basis to a basis. And by something we talked about, a mapping, and now just think of what the standard basis by that matrix gets mapped to the first column, second column, third column, etc. So that basis goes to basis. So let me write those two down. That's like the logic. But anyway, you almost don't have to, you almost forget the logic and just remember this is a fact that, as I say, you should have rolling off your tongue or head or something. So let's make a bit of space. So I'll write it in red here. So if det A is non-zero, then, and two different logics, at least. I mean, there's lots of other ways you could think. Logic 1 would be A is invertible. So maps, so it's an isomorphism. I'll put that in brackets, isomorphism from Fn to Fn. So maps basis to basis by week 3 or something, I think. So AE1 dot 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 AEN is basis, but these are just the columns of A. Another logic, both perfectly fine, just different ways of through the woods. So A, det A non-zero means reduced row echelon form of A is identity. So dimension of the column space, which is the rank, equals n, i.e. dim col A equals n, so columns are a basis. Or, I mean, yeah, that's good enough. Then when I said it earlier, I said then the nullity was 0, so it's injective, but I don't need to go through that rigmarole. I can just say it like that. All good? All right, good. Anyway, so that's a super important one. The determinant of A is 0 if and only if two columns of A are linearly dependent. Sounds a bit right, but there's something a bit suspicious, the like two-column business. Oops, down here. Because in R3, you could certainly have this vector and this vector are linearly independent. This one and this one are linearly independent, and this one and this one. So pairwise, any two are linearly independent, but the group of three of them is not linearly independent. Because linear independence of three things means A, there is an A, non-zero A, B, C, such that A times the first, B times the second, C times the third equals 0. And that's not the same as saying those ones are linearly independent, or those ones, or those ones. So this one's false, and that's because of the two columns. Okay. Let B be a matrix B. Okay, let B be a matrix that is obtained by first randomly permuting rows and then randomly permuting columns. Then the determinant is plus or minus det A, true or false? That one is true. Swapping any rows multiplies by -1. Swapping any columns multiplies by -1. So it'll just be an odd or evenness thing whether we're plus or -1. Certainly true. The matrix A is invertible if and only if the scalar, this guy is invertible in the field. Yep, true, good. Saying invertible in the field is just saying non-zero, and so that's our favourite thing, that something's invertible if and only if its determinant is non-zero. This next one you might recognise as something called the Vandermonde determinant. Which is useful at a few places, like with, I don't know what it's called, but when you're finding polynomials to fit points or something. And it's true. The point of that one, though, it's a nice, like, famous one. It's a not, you know, it turns up quite a lot. It's not completely arbitrary. But you certainly don't want to try to do it by just working out the determinant. It's a big fat mess. Ultimately, you will get there and see that it equals this. But, you know, you'll get some big sum of lots of terms and it's hard to see how to factorise. Instead, you should use a clever choice of row and column operations to try to just make it fall apart. And instead of doing it, do it for 3 by 3 first, but then why not do it for n by n there's an obvious pattern to this, of course. x1, x2, x3, call them that, so you can go up to xn, and then, you know, obvious what the pattern is. So this one is true, but I'll leave it as an exercise for you to it's a fun one to try to do. Use row, column, ops to prove, and I would recommend do the n by n case, which I guess you would do by an induction. But I think you can do it also, you know, you can see that you could do these row operations to reduce it down to some upper triangular matrix with just these products on the, these, wherever they are, these on the diagonal. But maybe you just want to do it by induction. So you want to reduce it down somehow to see that you can extract this factor times the determinant of a smaller Vandermonde. Anyway, that one's fun. So it's true. The next one is obviously true as well. The next one, is that true or false? True or false? Bit of arithmetic. The trick, if there is one that's being employed here, is the common mistake of saying determinant of 5 times a matrix is 5 times the determinant. Okay. It's not. It's 125 times the determinant because we're in 3 by 3. It's because that 3 is living in all of the rows, so row linearity, you have to bring it out of each row separately.
Is it like, would it have the 5 is like 5i, and then if you were to take the determinant of 5i,
Yeah.
you have the...
Good. Yeah, another good way of thinking of that is to write this as 5 times the identity, so 5, 5, 5, 5, and then it's clearer. You take out the determinant of that guy as 5 times 5 times 5. Yep, good. Okay, so the trick here is that so it turns out to be true, I think. 5a squared b is 5 cubed det a squared det b, which I think does equal 1500. But I'll highlight this 5 cubed and note det lambda a equals lambda to the n det a if a is n by n. Okay, very, very common mistake, that one. Yeah, the next one, well, it's sort of true or false depending on how you read it. As long as u and v are both over the same field, then yes, that's fine. I mean, you can just map the linear transformation that takes first basis to u1, second guy to u2, third guy to un. That's a linear transformation doing the right thing. Okay, so it's true. If they were over different fields, then you just can't talk about a linear transformation. So maybe it's sort of true or false. If they're over the same field, so assume same field, then true. Okay. So that just came from, we discussed at a certain time that linear transformations are just very, very free. I mean, they're, so you can just, you know, choose where pick a basis of your domain and just pick any old vectors you like in the codomain and send each of these to those vectors you chose earlier. That's a linear transformation. Here we're taking the special case with U, where these guys are even a basis of U. Okay. If the image isn't a basis, then we'll get it's still linear transformation, but it won't be injective anymore. Okay. Yep. So there's very, very free linear transformations. And we know they're very, very free because we showed that it's just isomorphic as a vector space itself to m by n matrices. n was the dimension of the domain and m the dimension of the codomain. So that's very, very free, just picking all of these coefficients freely in the matrix. All right, so that's sort of true-ish. If the nullity is 0, then the determinant is non-zero. True or false? It's indeed true. It's true for, again, various logics, but probably the best, neatest way here. Well, let's say it this way. Nullity being 0 means that you're injective. That's the definition of injective, almost, basically. And if you're injective between fn to fn, which is what this guy's doing, vector spaces of the same dimension, then you're also surjective, so you're invertible, so your determinant's non-zero. Alternatively, if the nullity is 0, then the rank is everything, which means your reduced row echelon form is the identity, and so your matrix has non-zero determinant, because it's some non-zero multiple of that by the row operation process. So yep, true. We're getting there. Let theta be a linear transformation and be a basis. Then this, well, that's just stupid, of course. You know, if theta has to be invertible for that to happen. And let A be this. Then A is invertible if and only if A cubed is invertible. So true or false? If you think in terms of determinants is probably easiest, maybe. Determinant of this is just determinant of A cubed. That's a non-zero field element exactly when determinant of A is a non-zero field element. Okay. True. So here I would probably use just det A cubed equals det A cubed. All right, there was another question, but I think, yes, it's just, oh, okay. This is like question 1, but now we've got an A and a B, so you just have to do A inverse times B, but same business. Anyway, we won't do that. Any questions? Yeah. Yep. This one here? Yep. Yeah, so just keep it down for 1 second. So the matrix of the keep it down for 2 seconds. The matrix representation of this linear transformation here with respect to this basis in the domain and this basis in the codomain is the identity matrix. But if you wanted to change a basis matrix with respect to the same in both, well, it's U and V are different, so you can't do that. Yep, that's the identity matrix. It's not the identity linear transformation by any means, but its matrix representation with respect to those two choices of bases would be the identity matrix. Yeah, good. So it's, yeah, really important. Identity matrix being the matrix of a transformation doesn't mean that the thing is the identity, unless you were taking the same basis in the domain and codomain. Okay. All right, good. Okay, see you next week.
Must be an end-to-end, is it? Because we must require the range to be equal to the code.
Which one is that, sorry?
I'm sorry.
Oh, this one. It's not really, it's end-to-end, this is false. So it is end-to-end if we're going to even talk about determinant, because we need it to be a square matrix. Well, or it needs to go from a vector space to another vector space of the same dimension. Otherwise it won't have square matrix. But also to talk about, sorry, I'll start again. When we're talking about determinants of a theta, it has to be an endomorphism. Yeah, so that has to be an endomorphism. But it is, because we're given that and that. But the reason this one is false is because It's only when theta is an isomorphism that the determinant is non-zero.
Right.
For example, let's take theta to just be the map that takes everything in Fn and squashes it to zero. Theta of everything is zero.
Okay.
That certainly has determinant zero, but it's a perfectly good linear transformation from here to here.
Yeah, so that comes back to my first understanding. So like, the range must equal to the codomain.
Oh, range, sorry, yeah, no, you're right, you're absolutely right. It has to be surjective, sorry. I thought of...
Was that a equivalent statement?
Yeah, so if you've got... Yeah, that's right. I mean, if the... well, you got to be a bit careful. So if you got theta from a n-dimensional space to like a 7, let's say f7 down to f5, you could certainly have that being surjective, range equaling the codomain, but it won't be invertible.
Okay, yeah, makes sense.
But it's when you've got f7 to f7, then if you're surjective, you're also injective.
Okay, yeah.
And therefore invertible and all that.
Thank you.
Okay, no worries.
Actually, question. Is
Maybe we'll discuss outside if that's it. Because
wait, should I just ask you in the tutorial later?
oh no, it's okay. Yeah, it's fine. Outside's fine.